Hi everyone, my name is Arjun Vijaywargiya. I am a postdoctoral scholar at UT Austin working within the CosmicAI Institute. My research develops reduced order models for dynamical systems arising in chemical kinetics. Specifically, I'm interested in quadratic systems as models that appear in important applications like combustion, systems biology, and astrochemistry, either already have this structure or contain nonlinearities that can be lifted to a quadratic form. A central challenge in simulating these systems is their prohibitive computational cost, as these often tend to be high-dimensional, parametric, and extremely stiff. This high cost motivates the development of surrogate models that reduce the computational burden without a major loss in accuracy. Reduced order models are one way to do this. They save cost by compressing the state into a lower dimensional representation and only evolving the essential dynamics. However, for nonlinear systems, traditional reduced order models can become inaccurate and even unstable. This happens as they rely on a projection step that inevitably leads to closure error due to the presence of unresolved modes. These modes remain strongly coupled to the resolved ones through the nonlinearity. In fact, one can formally show that the unresolved influence makes the resolved dynamics explicitly history dependent, where the past states collectively influence the present dynamics. To get around this defect of traditional models, I'm developing a memory augmented model that accumulates the unresolved influence through additional noise and memory terms that account for the closure error, restoring both stability and accuracy. In our latest preprint, we show that the memory effects are non-trivial, even for linear systems. We develop inverse problems that enable a data-driven recovery of the model operators and identify conditions under which these remain well posed. We also propose an efficient numerical solver. When tested on a representative test case, we show that the memory model accurately reconstructs the true trajectories, where a memoryless model completely fails. I'm currently extending this methodology to incorporate quadratic structure so that it can be applied to model-reduced chemical kinetics. Thank you for listening.